Alright, so let's go back to induction. So remember the basic setup for induction. Given the following, given that P of n implies P of n plus 1 for all n bigger than or equal to 1, and given that P of 1 is true, we can conclude P of n is true for all n bigger than or equal to 1. That's the essence of mathematical induction. So to prove a family of propositions P of n is true for all n, we only have to show two things. We have to show a base case like P of 1, and then we have to show this inductive step. We have to show if P of n is true, then P of n plus 1 is true. If we can do those two things, then we can claim P of n is true for all n bigger than or equal to 1. And the 1's not magic. We could do this for all n bigger than or equal to 5 as long as we prove a base case P of 5. Or all n bigger than or equal to 0 as long as we show a base case P of 0. Or we could do this for even numbers by starting with P of 0 and showing P of n implies P of n plus 2. Right? So you can find different versions of this, but this is the essential idea. And this first piece is called the inductive step. And the second part is called the base case, or the basis. So we went through an example of this on Monday. We showed that the sum of consecutive integers 1 through n is equal to n times n plus 1 over 2. And let me do that example again, but we'll do a bunch of examples like this. So let P of n be the proposition 1 plus 2 all the way up to n equals n times n plus 1 over 2. And we want to prove P of n for all n bigger than or equal to 1. We want to prove this formula always works. P of 1 says basically 1 equals 1 times 2 over 2. And that is correct. The formula works for n equals 1. Right? If we set n equal to 1 and we plug it into here, it's 1 times 2 over 2, that's 1. And that's the sum of the first 1 integers. So P of 1 is true. So now suppose P of n is true for some n bigger than or equal to 1. We want to prove P of n plus 1 is true. Okay, if P of n is true, that means that the following is also true. All right, because that's what P of n says. When I have two expressions that are equal to each other, I can do things to both sides and maintain that equality. I can add 5 to both sides, I can multiply both sides by 3, I can do stuff as long as I do it to both sides. Equality still holds, right? So here's what I'm going to do. I'm just going to take the left side, and I'm going to add n plus 1. And I'm going to take the right side, and I'm also going to add n plus 1. And does everybody agree that those two things must still be equal to each other? Right? As long as these things were equal, which was our assumption, these have got to be equal. But now I'm just going to go crazy with some algebra. So this is going to be n squared plus n over 2 plus 2n plus 2 over 2, which is n squared plus 3n plus 2 over 2, which is n plus 1 times n plus 2 over 2. That's just algebraically manipulating this right side into an equivalent, simpler form. But now I've shown that this sum, which is the sum of all integers from 1 through n plus 1, is equal to n plus 1 times n plus 1 divided by 2. Well, that's exactly what p of n plus 1 says. P of n plus 1 says the sum of integers from 1 through n plus 1 is n plus 1 times n plus 2 divided by 2. We just proved p of n plus 1. So we can say, therefore, p of n plus 1 and so now we know p of n implies p of n plus 1. And so we've proven our basis case, and we've proven our inductive step. And by mathematical induction, we can say, therefore, p of n for all n bigger than or equal to 1. And the reason is mathematical induction. And that's our QED. So let's just keep going with this. Let's look at the sum of odd integers. So if we add up the integers 1, 3, 5, 7, 9, and so on, up through, let's say 2n minus 1, the claim is this is equal to n squared. So how do we prove this? Well, make a family of propositions. Let p of n be the proposition 1 plus 3 plus 2n minus 1 equals n squared. So what does p of 1 say? It says the sum of the first one odd integers is equal to 1 squared. And that's definitely true. If we want to check, we could try p of 2. P of 2 says the sum of the first two odd integers, 1 plus 3, should be 2 squared. Well, that's also correct. 1 plus 3 is 4. P of 3 says the sum of the first three odd integers, 1 plus 3 plus 5, should equal 3 squared. 1 plus 3 is 4, plus 5 is 9, that's equal to 3 squared. So I mean, this seems plausible. It works in at least 3 cases. But we want to prove it for all possible values, and we don't want to have to do this for every possible integer n, because that would take an infinite number of lines. So we use mathematical induction. So all we have to do is prove p of n implies p of n plus 1 for any n bigger than or equal to 1. Okay, so let's prove that. So we'll start off with p of n. That's an assumption. And p of n says this thing. 1 plus 3 plus dot 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 plus 2n minus 1 is equal to n squared. That's the definition of p of n. So generalizing what we did in the last proof, any ideas what we can do for step 3 here that might move us in a helpful direction? And we never know what to do. This is kind of a guessing game. It's a trial and error thing. You get a hunch or you get desperate and you just do random things and hope something helps. But any ideas here?
We'll start with the summation that goes up to 2n plus 1.
Okay, why?
because that's what we have to prove equals n plus 1 squared.
Okay. So, let me show you a trick you can do. Remember I've said everything that you put in your proof has to be logically true, has to follow from what you've done before, or it has to be an assumption or a hypothesis, right? Okay, so here's what you can do. You can draw a little squiggly line and you can label a section of your page ignore. And I won't take off points for anything that you put in the ignore section. Okay, you can write down things that aren't true, you can write down things you haven't proven, you can say Nick dresses funny. I won't take off points for what's in there. But here's what you can do in here. You can write down, what are we trying to do? We're trying to show p of n plus 1. Okay, what does p of n plus 1 say? Well, it says 1 plus 3 plus 2n minus 1 plus one more odd number, which would be 2n plus 1, should be equal to n plus 1 squared. Now, if I write that over here, your proof falls apart because we haven't proven that yet. That's what we want to prove. But I'm writing it down so I can look at it and say, well, I know this. Can I somehow go from here to showing this? And you might get the insight that Randy had, which was, well, what if we added 2n plus 1? That would turn this left side into that left side. It doesn't turn this into that, but it makes the left sides look the same. So let's see what happens if we add 2n plus 1. And this is one of these, like, you know, trying to solve the puzzle by trying different things. So let's do that. So all we've done is add 2n plus 1 to both sides. Now if we could make this right side look like this, now we're in business. Because then we'd show that that's equal to that. That's pn plus 1. Well, guess what? N squared plus 2n plus 1, we can rewrite that by using more algebra. And if you don't have this step right here, if you just go directly from here to here, your proof doesn't hold up. Because there's no direct way that this comes from that. Right? Unless you assume the reader of the proof is astute enough to know that if you take this and add 2n plus 1, it turns into that. But again, don't assume the reader knows as much as you do. Don't assume that they've got the same insight. Spell it out for them. Right? I'm adding the same thing to both sides. Now I'm using algebra to reduce that into this form. And now you can say p of n plus 1. That's the definition of p of n applied to step 3. Because p of n plus 1 says add up the odd numbers up to 2n plus 1, or 2 times n plus 1 minus 1, which is 2n plus 2 minus 1. That's 2n plus 1, and that's equal to n plus 1 squared. So now you can drive it home. P of n implies p of n plus 1. And then p of n for all n, and that's mathematical induction, and then throw on your QED. Don't just stop here, right? Because you've taken the reader up to like the punch line. Hit them with the punch line. P of n implies p of n plus 1, therefore p of n is true for all n bigger than or equal to 1. So don't be afraid to whomp the reader over the head with this. All right, making some sense? So we'll do one more mathy one, and then we'll do a non-mathy one. Let's look at what happens when we add up powers of 2. So 1 plus 2 plus 4 plus dot 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 plus 2 to the n. And I claim that's equal to 2 to the n plus 1 minus 1. Do we know that this is true already? as computer science students, how do we know it's true? Where has this come into play for us? Binary. Because if I have a binary number that consists of a bunch of ones, there's 7 ones. This is 2 to the 0 plus 2 to the 1, 2, 3, 4, 5, 6. It's 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. And we know that's 1 less than what? This, which is the next power of 2. So this is the sum of all those first powers of 2, and that's equal to the sum, that's equal to the next power of 2 minus 1. So this is something we've already grokked, even if we don't know it. But let's prove it. So we'll make a family of propositions, P of n. P of n is the proposition 1 plus 2 plus 4 up to 2 to the n equals 2 to the power n plus 1 minus 1. All right, is P of 1 true? P of 1 says if we add the first power of 2, that should be equal to 2 to the, well, so, yeah, let's do P of 1. P of 1 says go up to 2 to the 1. So 1 plus 2 should be equal to 2 to the 1 plus 1 minus 1. All right, this left side is 3, the right side is 2 to the 2 is 4 minus 1, which is 3. 3 is equal to 3. So P of 1 is true. Turns out P of 0 is true also. But we'll stick with 1. Okay, so we want to prove this is true for all n bigger than or equal to 1. So we proved a base case, P of 1. Okay, so now we have to prove P of n implies P of n plus 1 for all n bigger than or equal to 1. Okay, well, step 1 is almost always the same. Assume P of n is true. Step 2, write out what P of n is. All right, that's the definition. Step 3, who knows? So let's make our ignore section. And let's see what P of n plus 1 says. P of n plus 1 says if we add up the powers of 2 up through 2 to the n plus 1, we should get 2 to the n plus 2 minus 1. So that's what we want to show. We want to show this equality. We've already shown a different but similar equality. And again, it kind of jumps out, well, what if I just add 2 to the n plus 1 to both sides of this? The left side's suddenly going to look like the left side of what I'm after. And the right side, maybe we'll get lucky. So let's do some algebra. All right, and this is absolutely an equality because all I've done is add this one term to both sides. But how can I simplify this right-hand side further?
You say 2 times 2 to the n plus 1.
Yeah, I've got 2 to the n plus 1 plus 2 to the n plus 1 minus 1. I just changed the order of these things. But something added to itself is just that thing multiplied by 2. And 2 to the n plus 1 times 2 is 2 to the n plus 2. And hey, that's exactly what we were trying to show. So it's the same punchline as always. P of n plus 1. And so P of n implies P of n plus 1. Therefore, P of n for all n bigger than or equal to 1 QED. I always run out of space at the bottom of these. All right, questions so far? And I don't expect this to flow easily at this point, right? If this is the first time you've sort of dealt with mathematical induction in this way, it usually feels a little bit mysterious, a little bit like either this is totally obvious, or I don't see how this is actually proving anything, or how is this different from just proving something else, right? But we're going to work with this for a few days, and we're going to work with it in different domains, and we're going to switch up domains right now and see a very different version of proof. So let's talk about a game. So imagine a floor which is covered with identical tiles. They're all the same size. And you have little plastic pieces in different shapes, and you want to put these pieces down on top of different tiles. And they fit, you know, very nicely. They're pieces made out of little blocks that are the same size as these tiles. And you can form different letters and pictures out of these tiles by putting down these shapes on top of the tiles and so on. And you can try to cover the entire floor with these tiles without any overlap. Right? Now if you allow the pieces to overlap, you just throw them all down. That's not as much fun. But if you take these tile pieces, you can try to cover the floor in a way that there's no overlap but everything is tiled. And we're going to have an infinite number of tiles that look like this. That's not a very accurate picture. Let me do it like this. They look like 3 tiles, kind of shaped like a funny looking L, like that. And using these pieces, we want to try to cover all the tiles on the floor. And you can put this down in any orientation that you want, okay? 90, 180, 270, or 0 degrees. And you're not allowed to have part of this outside the floor, and you're not allowed to overlap pieces. But you know, certainly if I take another one of these pieces and I flip it over, I could put that right here. And so if I had a 3x2 floor, I could tile it nicely with these L-shaped pieces. And I could do 2 of these across so I could get a 3x4 floor and cover that, and so on. And the question is, what floors can we tile with these L-shaped pieces? And so here's a theorem. If the floor that you're trying to cover has a square shape, and the number of tiles across and up and down is a power of 2. And if you have exactly 1 square anywhere that you don't want to cover, that's the square where the water pipe comes out, right? So you don't want to cover that, but you want to cover everything else except that 1 square, you can always do that with these L-shaped pieces, without any overlap, without going outside, and without leaving anything uncovered except that 1 square. And it doesn't matter where that 1 square is. So let's write that as a proposition, and then let's take a 4 or 5 minute break. So let P of n be the proposition. a 2 to the n by 2 to the n tile floor with one spot removed can be perfectly tiled with L-shaped pieces. And we want to prove P of n for all n bigger than or equal to 1. All right, take a 2 or 3 minute break if you want. Clear your minds, and then we'll see a proof for this using mathematical induction. All right, so let's prove this proposition. And there's going to be very little mathematics involved per se, at least in terms of equations and algebra. There's going to be some hand waving here, but hand waving is legal if you do it in a logically correct way. And I wouldn't ask you to do a formal proof on something like this because I don't want you to have to hand wave on paper, but these kinds of things are useful to get our brains away from the idea that there's got to be math, there's got to be some addition or multiplication or something algebraic going on for this to work, right? There doesn't have to be. So let's see how we could prove this. So P of n is a proposition that on a 2n by 2n tile floor with one spot removed anywhere in there, we can tile the remaining spots perfectly with these L-shaped pieces. Okay, well let's start with a base case. P of 1 says a 2 to the 1 by 2 to the 1 tiled floor, so a 2 by 2 floor with one spot removed can be tiled. Well, let's look at a 2 by 2 floor. And if we're going to remove one spot, there's only 4 spots to begin with, so we've only got 4 possibilities here. We could take out this spot, this spot, or that spot. So if we can show that each of these scenarios can be tiled perfectly with these L-shaped tiles, we're done with P of 1. And that's pretty easy, right? The tile, as I've shown it here, tiles this floor perfectly. If I turn it a little bit counterclockwise, it'll tile this floor. If I turn it a little more, it'll tile this one, and if I turn it one notch clockwise, it'll tile that 4th one. So by looking at all the possibilities for a 2 by 2 floor with one spot removed, we can exhaustively prove, yes, in all those cases we can tile it perfectly. And so P of 1 is true. So we got our base case done. We're halfway there. right, the trickier part is the general case. So let's assume P of n. So if we're assuming P of n, that means a 2n by 2n tile floor, with one spot removed, can be tiled. Okay, so let's make a 2 to the n plus 1 by 2 to the n plus 1 tile floor. And we don't know what n is. But whatever this floor is, since the number of tiles here is 2 to the n plus 1, and the number of tiles here is 2 to the n plus 1, I know that if I split each side in half, this is 2 to the n, this is 2 to the n, this is 2 to the n, this is 2 to the n. And so each of these quadrants is a 2 to the n by 2 to the n piece of flooring. Okay, and for P of n we need to remove one spot from the floor somewhere. Well, let's just suppose that we remove this square right here. Doesn't matter where it is. But let's suppose we remove a square from somewhere in that upper left quadrant. What do we know immediately about what we can or cannot tile?
That upper left quadrant.
We can tile that upper left quadrant. Why? Because we're assuming P of n, and P of n says a 2 to the n by 2 to the n with one tile removed can be tiled. So we can tile all of this. Why? Because P of n is true. That doesn't help us with these other three quadrants because they don't have any missing pieces. Any ideas?
Remove a little square from each of the little quadrants.
If we removed a little square from each of those quadrants, we could tile each of those. And we'd be left with 3 squares that we still need to tile. So here's what we're going to do. We're going to remove this square, and this square, and this square, temporarily. And with those removed, we can now tile all of this. Why? Because Pn is true. And we can tile all of this because Pn is true. And we can tile all of this because Pn is true. But we're not quite done. We still need to tile this little L-shaped piece in the middle here. Can we do that? Yeah, just throw one L-shaped piece down on top of that. And now that's been tiled. And the whole floor is now tiled except for that one square that was missing in the beginning.
But that doesn't prove what we're trying to prove, does it?
Well, it proved that if we had a 2 to the n plus 1 by 2 to the n plus 1 floor with a tile missing from this quadrant,
Oh, it does.
we can tile everything.
Yeah.
But if the tile's missing from this quadrant, we haven't shown anything yet. But we can repeat what we just did, but cover this with p to the n, take out a little L-shaped piece here, and then cover that. And so you've got 4 cases you have to show, but after you've done each of those 4 cases, you've proven that in all possible situations you can tile 2 to the n plus 1 by 2 to the n plus 1. Therefore, you've shown p of n plus 1 is true.
My initial thought was that is that we had to take one little square out of the upper left-hand quadrant and one square out of the upper right-hand quadrant and so on.
Okay.
But when you've taken one little square out of the upper left-hand quadrant, you've taken it out of the whole.
Exactly.
thing.
Right. Right. So that's the setup. So we've shown if p of n is true, p of n plus 1 is true. And therefore, together with the basis case, we've shown p of n for all n bigger than or equal to 1.
So again, my initial thought was when you picked those special little squares, that was not good because you had to have kind of an arbitrary
Right.
thing. But it was the little square that you removed
That was the arbitrary one, right? And these actually do get tiled. They just get tiled at the end of the process.
Right. Well, the square that's blotted out was the arbitrary one, but then after that, you had the choice of those others.
Right, right.
Which was not what I thought when you started to do it.
Okay. All right, so this is a little weird, right? This is a different kind of beast from, you know, the sum of odd numbers is n squared. But it's still using mathematical induction.
Where was the hand waving? I didn't really see.
And I'm always waving my hands, even if I'm not. So to make this formal, you would need to do a lot of writing, right? You'd need to thoroughly explain why this covers all of the squares there, and that you take those out and those get covered, and then you have to, you know, do the rotation of the piece and cover this, and then you have to generalize it 3 more times, and so on. So that's kind of the hand wavy part.
Well, the essence of the proof is there.
But the essence of the proof is there, right? And it's mathematical induction. It's using the proof for n to get to the proof for n plus 1. Here's what I want you to think about, and this is a real punchline for the course. P of 1 we showed exhaustively. We had 4 cases, right? So 2 by 2 floor, we showed how to do that by looking at all the possibilities for removing one tile from a 2 by 2. Now suppose you find yourself on your favorite desert island, and it's the desert island where the tiling boat washed up, and so there's tiled floors and there's tiles. And you have a 4 by 4 floor in your hut, and you have these L-shaped pieces, and you've got a tile missing, I don't know, like right here, for your water pipe, think Gilligan's Island, and you want to tile this with L-shaped pieces. Well, you remember in 215 you saw a proof that you could do that, but we never actually talked about an algorithm for doing it. But how would you prove to yourself that you could tile this? Split it into 2 pieces, and then tile this using the fact that we know how to tile a 2 by 2. Well, how do we do that? We just look at all the possibilities. And a 2 by 2 with this thing removed, we said just rotate this thing to the right and drop that into place. So we take this tile and we pop it down right here. And then we said go into the other 3 quadrants and temporarily remove these corners. And use your algorithm for tiling a 2 by 2 to tile this and this and this. Well, we can do that because, again, lower right corner missing, just rotate this thing right and tile that. And upper right missing, take this thing and rotate it counterclockwise 1 spot, and now we have a tiling there. And then upper left missing, take this piece and rotate it twice counterclockwise, and we can tile that 2 by 2. All we've done is tile a bunch of 2 by 2s, right? And then we said you've still got 3 pieces in the middle you haven't covered yet, but it's shaped like an L, so just take your L-shaped piece and cover those. What did we just do? We just tiled a 4 by 4. Knowing nothing more than how to tile a 2 by 2 and this kind of odd little proof that we can do this tiling. All right, so you open up a shop on the island and you say, I will tile your 4 by 4 floors for you. Bring me your 4 by 4 and I'll tile it. And your friend, who was also on the boat, thinks that's a good idea, so they open a bigger tile shop and they say, I am the 8 by 8 tile shop. I'm going to tile 8 by 8 floors for you. Give me an 8 by 8 floor and I'll tile it. How are they going to do that? Somebody's going to come to them and they're going to bring their floor, and it's going to be an 8 by 8, and they've got a square missing somewhere, and they're going to say, hey friend, can you tile this for me? Here's what they got to do. They say, sure, come back tomorrow. Okay, they take the 8 by 8 floor, They split it into a bunch of 4x4 pieces.
Feel mighty money.
Yeah, they're going to take this, they're going to bring it to my shop and say, hey, here's a 4x4, can you tile it? I'll give it back to them. And then they're going to block these out. Bring this to my store, can you tile this one? Yeah. Can you tile that? Can you tile that? Yes. They get those 4 solutions back, and then they pop one more tile down here. And now they've tiled the 8x8, and they can sell that to the person for like 10 times the price of what they paid me to do a 4x4. Now you can see where this is going, right? Somebody on the other side of the island opens a 16x16 shop, and they just outsource the 8x8 pieces to my friend, who outsources the 4x4 pieces to me. And maybe I have a pet mouse or something that knows how to do the 2x2 pieces, right? And nobody's ever really doing any work. Nobody knows what the magic algorithm is for tiling a 1024 by 1024 floor, but you can absolutely do it. All you got to do is break it into 4 problems of 512 by 512. And if you don't know how to do that, just break each of those into 4 problems of 256 by 256, and keep doing that until it comes down to, you know, a gazillion 2x2 problems. And we know how to do this, just rotate the tile in the right way and plop it down. So we've proven this proposition P of n for all n bigger than or equal to 1, but in so doing we've also inadvertently come up with an algorithm for performing this process. And this is classic with inductive proofs. They can be used to prove that something is a certain way, but they also give us an algorithm. And this is why mathematical induction is going to tie right into programming in CSE 222. Because a lot of the algorithms we do in 222 are what we call recursive algorithms. And recursion is basically solving a big problem by breaking it into smaller problems and getting somebody to solve those smaller problems for us. Now what's the trick here? I'm actually alone on the island, right? My little talking mouse and my friend who crossed the island and so on, that's all me. And when I want to tile a 16 by 16 floor, I'm the one who breaks it into 4 8x8 pieces and tiles each of those. And how do I do those? By breaking them into 4x4. And how do I do that? By breaking them into 2x2. And that's what's going to happen with recursive code. We're going to have one function, tile, and when we call tile of 16, that function's actually going to call tile of 8 4 times and solve the problem for 4 8x8 sections of flooring. So hopefully that sounds a little weird, because it is very weird. And we're not going to do a lot with recursive programming in here. We'll do a lot of it in 222. But this is where this stuff is going to lead us. But we will do a lot more proofs by mathematical induction continuing on Friday. And we'll tie these things back to algorithms as we walk through these. So keep that in mind. So I want to discuss next time some more things we can prove with mathematical induction. I want to do some postage stamps problems. These are classic problems trying to prove that you can make any postage with certain sizes, certain denominations of stamps. Or for example, if you have an unlimited number of pennies, nickels, dimes, and quarters, you can make any amount of change that you want, right? Turns out you don't need pennies. You could do it with other denominations, but some denominations don't work. They leave you with amounts of change that you can't make. So we'll do some proofs on what you can or can't make change with certain denominations, and that'll turn into algorithms also. And then we'll look at some false proofs. We'll prove that all horses in the world are the same color, and we'll use mathematical induction to show that, and we'll figure out why that's a false proof. And we'll talk about pie fights. And there's a nice mathematical proof we can use for people having a very peculiar type of pie fight with one another and seeing who gets hit with pies in the face and who doesn't. So we'll play with a bunch of these things on Friday. And we'll continue induction definitely into next week. I'll probably post some homework questions on Friday related to induction, and they won't be due until the following Monday since we only have one meeting next week. So we'll talk about that next time. All right, so I'll see you then.